Welcome back to Control System Lectures. Just to let you know, I've decided to drop the prefix on the video titles because they were taking up too much real estate. But these videos are in the same series of lectures, so if you're subscribed to Control Lectures, you'll still receive these updates. This video is a continuation of the Introduction to Bode plots that I posted last week, and here I'll discuss how to sketch a Bode plot by hand directly from the transfer function. And this first video will only cover when the transfer function is a constant gain. Now you might be asking yourself, why do we need to learn how to sketch Bode plots by hand when we have computer programs such as MATLAB that can generate a Bode plot with the touch of a button? I've been a controls engineer for over 10 years now, and to be honest, I very rarely ever had to sketch a Bode plot by hand. But while you might never actually need to do this, there are still at least two compelling reasons to learn this skill. The first is that by practicing this, it gives you an intuitive understanding of how poles and zeros affect the frequency response of a system without having to actually ever plot the response. And the second is that it gives you the ability to estimate the transfer function just by looking at the frequency response of a system. And this is particularly handy when you're trying to estimate a transfer function, say from the output of a frequency sweep on a new structure that you're building. So recall now from the introduction to the Bode plot video that when you have a transfer function, h of s, you can calculate the steady-state frequency response by setting s to j omega. Then you can solve for the real component and the imaginary component and rewrite h of j omega as just the real component plus the imaginary component times j. If we were to plot this on a real and imaginary axis, where the real component is just drawn on the horizontal line and the imaginary component is drawn on the vertical line, the gain of the transfer function for that particular frequency is just the length of the line from the origin to that point on the real imaginary axis. That can be written as the square root of the real part squared plus the imaginary part squared, or in shorthand notation you can just put these two vertical lines around it, which means the magnitude of h of j omega. And the phase is just the angle of the vector off the positive real line. And we can write this as the arctangent 2 of the imaginary part and the real part. And in shorthand notation, you can just write this as the argument of h of j omega. We can establish the sign of the phase by which side of the real line it appears on. In this case, it might be about 45 degrees. If we continue it a little bit further, it might be 120 degrees. But if we go down below the real line, then it becomes negative, so negative 60 degrees in that case. So let's review the simplest transfer function there is, which is a constant, and see how that is represented on a Bode plot. In this case, the transfer function, h of s, is just equal to k, which can be any real number, either positive or negative. And we can represent this in block diagram form by showing that the input gets multiplied by k and becomes the output, or u of s is the input and y of s is the output. Now we can apply the gain equation from above, which is the magnitude of h of j omega, to this constant k, which is just the magnitude of k, which is a positive k. And the phase, which is the argument of h of j omega, is equal to the arctangent 2 of the imaginary part, which in our case is 0, and the real part, which is k. And again, k can be either positive or negative. And that's why we're using arctangent 2 to keep track of the sign. Let me explain it this way. If we were to plot this on the real and imaginary axis, then all of the values would lie on the real line since there is no imaginary component. If k is a positive number, then it'll appear on the right side, and if it's a negative number, it'll appear on the left side. But one thing to note about both of these positions is that whether k is positive or negative, the point still exists exactly a k distance from the origin. And since gain is the distance from the origin, the gain is always k for constants, whether they're positive or negative. Phase, on the other hand, is different. For the first value, a positive k, phase is 0 degrees, but for a negative k, it's 180 degrees off the positive real line. Traditionally, we would just say minus 180 degrees, but they're equivalent. So if the constant is positive, then the phase is 0 degrees, and if the constant is negative, then it's minus 180 degrees. And that's why I like to use arctangent 2, because it keeps track of the sine of k for you, so you don't have to think about that. If you just use arctangent, you'd have to remember to subtract 180 in certain cases and not in others, but I'd prefer not to remember that and just use arctangent 2. So now that we have our gain and phase, how can we represent this on a Bode plot? Well, the gain is easy. Like we said before, it's just k for all frequencies. But to plot it on a Bode plot, we have to convert it into decibels, which is just 20 times the log base 10 of the magnitude of k. And again, it's constant for all frequencies, so it's just a horizontal straight line. And luckily for this example, phase isn't much more difficult. Phase is 0 degrees when k is positive, and it's minus 180 degrees when k is negative. But again, the phase stays constant either at 0 degrees or at minus 180 degrees. It stays constant across all frequencies. So if it's not too intuitive looking at this at a Bode plot or on a real and imaginary axis, another way to think about this is just to input a sine wave through the block diagram. A sine wave input produces a sine wave output whose amplitude has been adjusted by a factor of k. Also, if the input was a positive sine wave and the k was a negative 1, the output would just be flipped along the vertical axis like this. Of course, as you can see, this is just a phase shift of negative 180 degrees. So let's do one last example, and this is with a very simple electrical circuit. Let's say you had a voltage generator whose output was a sine wave. And the positive voltage was then applied to a resistor, and both of them were tied to ground. The resistor has resistance R. A current would be induced, I, and using Ohm's law, we know that V equals IR. But if we wrote this as voltage changed over time, it would be V of time equals I of time times R, since resistance wouldn't be changing. We could take the Laplace transform of this equation and then solve for the output I over the input V and get 1 over R, which is the transfer function for this simple circuit. And since the resistance isn't changing with time, 1 over R is just a constant, and we could represent this on a Bode plot as a constant gain at 1 over R with a phase shift of 0 degrees. I know it's 0 degrees because R is going to always be positive. So this is what the Bode plot would look like for a very simple constant transfer function. Of course, most transfer functions aren't this simple. They can be made up of any number of complex or real poles and zeros. But the step-by-step example here of how we go about generating a Bode plot still holds up for those other parts. And so what I'll do in the next couple of videos is expand on all of those different types of transfer functions and then show you how to approximate them very easily using just a few simple concepts. And since the next few videos all tie together nicely, I'm not going to wait a week to put them out. I'll try to get most of them out over the next couple days. So if you don't want to miss anything on how to sketch Bode plots, don't forget to subscribe. Thanks for watching.